Welcome back to channel. In last video we have seen construction working of Francis turbine. In this video we will see our second reaction turbine, that is Kaplan turbine and draft tube. Okay. So Kaplan turbine, it is first hydraulic turbines, that means input power is from water. Okay. It is axial flow turbine, means at entry puts the rotor is the axis, entry is axial, outlet is axial, so it is axial flow turbine. It is again reaction turbine, that means at inlet it is having both pressure energy as well as kinetic energy. Then it is suitable for low head and high discharge. Then shaft of hub or rotor in case of axial turbine is always vertical, there is no horizontal axis. Kaplan turbine is there. So, and again its name is in honor of Austrian engineer V. Kaplan. They invented it. Okay. Now see its construction. In construction, it has main parts scroll casing. Okay, it means same scroll means again in similar to spiral, area of flow is decreasing in direction of flow. Okay, this is our scroll casing. This is the section view. So this total is our scroll casing, and if you see that in direction of flow this cross sectional area is decreasing here. Here diameter is more, here diameter is less. So in this direction, if you take consider totally, area of cross section is decreasing continuously in order to maintain velocity of flow constant, similar to Francis turbine. Then guide mechanism, here this is the guide blades, second number. Guide blades again same purpose as that of Francis turbine, to give proper direction to inlet velocity. Okay. Then hub and rotor, this is called as an hub or boss. Okay, this is the hub or boss for Kaplan turbine, and over which blades are placed. Number of blades are usually less, 4 to 6 numbers. In case of Kaplan turbine, blades are adjustable. In case of, there is another one axial flow turbine, that is propeller turbine. In that case construction all part is same, only difference is that blades are fixed and not adjustable. Then there is a draft tube. Here this is the draft tube which connects runner outlet to your tailless level below. This is the water level and it connects below tailless level. So construction is simple one for this Kaplan turbine. Velocity diagram is same as that of Francis turbine. Some important relations are which differs from Francis turbine are, first is it is axial flow turbine. Then discharge is along axis. Okay, here along axis, this is the axis, it is the area available for flow, and discharge is along this axis here. So area is cross area of this rotor. If we say dB is the diameter of boss or hub, outer diameter of rotor is do, then this outer diameter will be do, this diameter of boss, then area is pi by 4 d square, so do square minus base dB square into velocity of flow. Okay, for Kaplan turbine, velocity of flow at inlet and velocity of flow at outlet is same. In case of Francis, it is not always constant. Again u1 and u2, that is linear velocity at inlet and outlet for Kaplan turbine, are same, and they are calculated at outer diameter, not at hub diameter. So remember that in u1 u2 relation we have to use do, this is outer diameter and not boss diameter. So this is for Kaplan turbine. Its velocity diagram, construction velocity diagram and work done equation, it's same as that of our Francis turbine. So we will not repeating that part. Then next part is draft tube. Okay. So what is draft tube? Draft tube connects runner outlet to tailless level. Okay, it connects runner outlet to tailless level simply. Why it is used? It permits negative head, that is below atmospheric head, at runner outlet, and hence increases net head on turbine. Okay. What is meant by that? Let's see by diagram. Suppose this is the tailless level and our turbine rotor is at this height. Now above this will be the head or our turbine. Now let that we want to increase head. If we want to increase that head, then we have to move this rotor runner or rotors say towards this tailless level. It means if we want to increase this edge or position of rotor be nearer to tailless level or water level. So by moving this rotor downward side, we are increasing head or turbine. Now again, if we want to still increase head or power requirement, then we can go for this position. Here head is increased. If this is H1, H2 and this is H3, then here H3 is more than H1, so head and hence power output will be more. Then if we want to still increase head or turbine or power output, we will go below tailless level position. Here again head is increasing. Okay, what happens? Due to this arrangement, our runner is below tailless level. Below tailless level means below water level. So here if we want to take this runner outlet for inspection purpose or maintenance purpose, then we have to do great efforts. Okay, it is not a simple task. Then by using draft tube, we create same head at this position. Here if we use draft tube at here, we create same head, that is the head, extra head is this extra head is generated. This extra head is generated due to placing runner from this first position to this last position, that is fourth one position. So this extra head is created when we are going below tailless level here. But if you use draft tube, then this extra head is converted. Suppose this is the HX extra head, then this extra head is gained here only when we are using draft tube. Okay, that is we are creating negative pressure head here. How we create that negative pressure head we'll see in detail later. Okay, so this is the use of draft tube. Draft tube increases this extra head on turbine by converting the waste kinetic energy into pressure energy. Again, draft tube, by using draft tube, it is easy for inspection and regular maintenance of runner because it allows negative pressure at above tailless level. So inspection becomes easy, maintenance work becomes easy. And if you see construction, this is a simple tube with increasing area and direction of flow. Then there is a next point, what are the types of draft tube, important for exams. Then there are few types are here: simple conical, simple elbow, then circular inlet, rectangular outlet, Moody's spreading tube. So features of this is here alpha, that is this half angle is from 6 to 7 degree. If we increase more angle, then there will be chances of AD losses due to whirling motion. Okay, then this is the most efficient draft tube and simple construction. And this is a simple elbow type. This requires less space because it is bent. Okay, so it requires less space. Again, it is having about 70 to 75% of efficiency. Okay, Moody's spreading tube or Moody's spreading tube draft tube. Then here single inlet, two outlets are there. Purpose of two outlets is to reduce whirling velocity in draft tube and hence losses. Its efficiency is about 85%. Okay. Then simple circular inlet, rectangular outlet. It is having nearly about 75% efficiency and mostly used for Kaplan turbine. So these are the simple types of draft tube. Okay. Now we will see about draft tube theory. Okay. This draft tube theory. So yeah. Previously we have discussed that or said that draft tube creates negative pressure at runner outlet or draft tube inlet, and draft tube theory in here we are going to prove it is draft tube creates negative pressure at turbine outlet or draft tube inlet. So consider this point as 1, draft tube outlet as 2. This is the atmospheric condition. Height difference is hs. This height difference is y. Then apply Bernoulli's equation. P1 by rho g, V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2 plus HF is the losses in draft tube. Okay, now this height, if you take reference at this point, this height will be Z1 will be HS plus Y. So adding here. Okay, now for adjusting terms, P1 by rho g is equal to P2 by rho g plus V2 square by 2g minus bracket these terms. Then from hydrostatic law we know that pressure at this point P2 is equal to atmospheric pressure plus weight over this level. This is equal to rho hg. Okay, then divided by rho g we get P2 by rho g is equal to Pa by rho g plus here h is y. So we are replacing h by y. Replacing this value here, we will get is equal to P1 by rho g, Pa by rho g plus V2 square by 2g plus y minus V1 square by 2g plus hf minus hs minus y. So adjusting term here, we will get that P1 by rho g is equal to Pa by rho g minus these terms. Here from diagram it is clear that V1 as D1 is less than D2 or V1 is always greater than V2. So this term is positive. Again this is the height, so it is never negative. So it is always positive. So this term positive, this term positive. So our P1 by rho g is equal to Pa by rho g minus some positive quantity, that is Pa by rho g is always less than atmospheric pressure. So here we have proved that our pressure at one point is always below atmospheric pressure, that is draft tube creates negative pressure at turbine outlet. D1 is less than D2, so V1 is greater than V2 and HS is always positive, so P1 is always less than our atmospheric pressure. Hence we have proved that draft tube creates negative pressure. Now next point is draft tube efficiency. Okay. We know that at the outlet of runner water is having some velocity, which is considerable amount of velocity. If you not use this velocity, energy related to that velocity will be lost. In draft tube we are using that velocity to convert it into some useful pressure head. Okay, so in draft tube initially we are having v1 velocity, corresponding energy will be 1 half m v1 square kinetic energy. At outlet, if v2 is velocity, then energy is 1 half m v2 square. So out of total, some energy is losing here, okay, and some energy here in draft tube is converted into useful pressure head. And this ratio of maximum, this ratio kinetic head which is actually converted into pressure head. Okay. Draft tube efficiency is ratio of kinetic heads which is actually converted into pressure head to maximum available kinetic head. It's called as draft tube efficiency. We know that if v1 is the velocity at outlet of runner, then maximum kinetic energy available for conversion is v1 square by 2g. And if v2 is the velocity with which water is leaving from draft tube, then converted energy is v1 square by 2g minus v2 square by 2g minus hf, because this head is lost in friction which is not converted, and this head is in kinetic head, so it is not converted into pressure head. So converted head is this much. So our formula will be v1 square by 2g minus v2 square by 2g minus hf upon v1 square by 2g. So this is formula for draft tube efficiency. Again, we will look back at equation 1, and we have p1 by rho g is equal to pa by rho g minus v1 square by 2g minus v2 square by 2g plus hs minus hf. Now adjusting term in this manner, we will get v1 square by 2g minus v2 square by 2g minus hf is equal to pa by rho g minus p1 by rho g minus hs. Okay, now if we consider gauge scale, then in gauge scale atmospheric pressure is 0. Okay, and minus indicates vacuum pressure. So v1 square by 2g minus v2 square by 2g minus hf is equal to vacuum pressure pv by rho g minus hs. This negative pressure is vacuum pressure pv by rho g minus hs. Then our equation becomes, this equation becomes, we are replacing this term by this, we will get draft tube efficiency is equal to pv vacuum pressure head minus hs on v1 square by 2g. So this is the two relations for draft tube efficiency. Okay. So in this video we have seen construction working of Kaplan turbine, then some relations for Kaplan turbine, and important is draft tube. Draft tube is very important in case of Kaplan turbine. It increases net head over turbine by utilizing wasted kinetic energy into converted into pressure head. Thank you for watching this video. If you like this video, please subscribe our channel. If you have any comments and doubts, please contact us. Thank you.